Let me copy over the circuit. Again, now you evaluate VO by VGS. Okay, you can think of this circuit as producing some VGS because of Vs, and this VGS produces some VO. Okay. The current that flows here is of course GM VGS, and what we want is the voltage across RL. Okay. Then you have this current division between this resistor and this branch. Okay. So, that current is given by RD divided by RD plus the impedance of RL and C2 in series. So, that is the current that is flowing in this in the upward direction. So, the actual voltage across RL V naught is negative of this times RL, okay, which can be written as minus GM VGS times J omega C2 times RD times RL divided by 1 plus J omega C2 RD plus RL. Again, now assuming that C2 must behave like a short, okay, meaning what do we mean by that? We have evaluated V naught. When we say C2 must behave like a short, what we mean is this value of V naught must be the same whether we have this capacitance C2 here or we have a short circuit. And you see that if this number here omega C2 times RD plus RL is much greater than 1, then you can neglect this 1 here, okay, because this imaginary part has much greater magnitude, and then this J omega C2 will cancel off. What will we get? RD RL by RD plus RL, okay, that is RD and RL appear in parallel across this controlled current source. Okay. So, this is the condition that we need. Okay. This is as far as the output voltage is concerned. Now, you can also relate this to the other thing I said earlier. How to evaluate this is to identify the capacitor and the resistance across it. You null the source, you set Vs equal to 0. This VGS also becomes 0, okay, because there is no Vs driving this, this VGS becomes 0, and this GM VGS also becomes 0. So, that means this becomes an open circuit. So, what do we have? All we have is a capacitor C2 and RD and RL. Okay. So, across the capacitor C2 you see the series combination of RD and RL, and that is what this is saying. Okay. If I rewrite it differently in terms of the reactance 1 by omega C2, the reactance of the capacitor must be much smaller than the resistance across it, which is RD plus RL. Okay. So, that is how you can choose C2, and as before you calculate the constraint on C2. C2 must be much larger than a certain capacitance C naught, and if you in the practical circuit use about 10 times C naught, that is usually good enough. Okay. Now, this is perfectly all right as far as V naught is concerned, but there could be a slight problem with this particular choice of C2 that I will show. Let us evaluate this Vd which appears between the drain and source of the transistor, that is the incremental Vd. Everything here is incremental, this is the incremental equivalent circuit. If I do that, what is that? This Vd is nothing but this current flowing into the parallel combination of Rd and this series branch. Okay. So, Vd by Vgs equals minus Gm times Rd times RL plus 1 over j omega C2 divided by the sum of everything Rd plus RL plus 1 by j omega C2. Okay. Now, previously we had only RL in the numerator for VO. Okay. If you look at this expression, so the bottom line is the drain voltage magnitude will be greater than the output voltage magnitude. Okay. And this is especially so if R D is very large. Okay. So, let me rewrite this as minus G m one plus j omega c 2 R L 1 plus j omega c 2 R D plus R L. Okay. So, now you see that you have this extra factor of 1 here. If R D is very large, the drain voltage can become much larger than the output voltage. Okay. As far as the incremental equivalent circuit is concerned, there is no problem at all. Okay. If you satisfy the earlier condition, you will get the value of V naught, which is minus G m times R D parallel R L times V G S. Okay. But in practice, you also do not want the voltage across the transistor to become very large, because it is after all a nonlinear device and that will cause nonlinearities. Okay. So, in this case you have to satisfy both conditions. Okay. That is, you want the voltage here to be equal to VO, okay, not much larger than VO. In this case, you have to satisfy both conditions. You want this number to be much more than 1 and this number to be much more than 1. Okay. That is omega c 2 R L to be much more than 1 and omega c 2 times R D plus R L to be much more than 1. And you clearly see that this is the stronger condition as far as C 2 is concerned. Okay. And if R D and R L are about the same magnitude, these two are about the same. Okay. If R D is equal to R L, this is 2 times that. So, it is not a big problem. But if R D is 10 times larger than R L, what can happen is you could satisfy this condition, not that one. Okay. So, typically on the output side, you try to satisfy this condition, that is omega c 2 times R L being much more than 1. The reason I went through all of this calculation is to make sure that this is not for the output voltage. The output voltage will come out just fine even if you satisfy this one. This is just to make sure that the drain source signal voltage equals the output voltage. Okay. So, I hope you understand exactly how these criteria are arrived at. Okay. Essentially, it is like evaluating time constants, which you would have done in some basic electrical circuits course. As I said, please revisit that. You need to know sinusoidal steady state analysis or phasor analysis in order to do these things fluently. And once you do that, once you understand these things, for first order circuits, which is what we most often encounter, the criterion is really easy. Okay. You identify the capacitor, you identify the resistor across it and make sure that the capacitive reactance is much more than the resistive. The capacitive reactance is much smaller than the resistive reactance. Now, one last thing, when you have multiple capacitors, what do you do? The easiest thing is, you could calculate the entire transfer function with multiple capacitors all together. It can lead to very messy expressions. So, what you do is the following: you take one capacitor at a time, and for calculating the value of that capacitor, while doing that, assume all other capacitors are shorts. Okay. This way, you will only have to consider first order circuits. Okay. And each of these is only going to give an inequality. It says that capacitor has to be much larger than something. So, you make it 10 or 20 times larger than that and everything will be fine. Okay.